Now that we've seen one binomial experiment, let's keep practicing and testing whether other probability experiments qualify as binomial. And then if they do, we're going to have to explain what they do and what their n, their x, their p, and their q are. All right, so let's start with the first one. A student takes a multiple choice test and it has 20 questions. Each question has 5 choices, only one of which is correct, and the student's going to guess randomly at each answer. Okay, well, that's going to be binomial. Let's prove it though. So the first thing you have to check is there a fixed number of trials? Right, that's the first criteria. And yes, you have to write out your criteria. So number 1, is there a fixed number of trials? And the answer to that is yes, right? It was performed 20 times because there's 20 questions on this quiz. That's your n value, right? And it's fixed. You're not changing how many questions there are on the test, even though you didn't study. Number 2, are the trials independent? Well, yes, and it's because the student is randomly guessing. So we have to explain. Because the student is randomly guessing. I just typed up the rest of these while I had a chance. So let's look at 2 disjoint outcomes. Do we have that? The answer is absolutely yes, we do, right? We have 2 disjoint outcomes. Now we have to say what they are. It's not enough just to say yes. You have to actually state what they are. So for us in taking a test, it's kind of obvious. Success would be getting the question correct, and failure would be not getting the question correct. All right, since those are our successes and failures, what we now need to think about is x. X is our random variable, which in this case would be the number that we get correct on the test altogether, right? Which could be as low as 0 or as high as 20, right? So it's number of correct questions that we get, right? Since successes are correct, that matters to us, right? That's going to be the number of correct questions, right? And then how low could it go? Well, it could go as low as 0, and then it could go 1, 2, you could get all the way up to, technically it's possible to get all 20 right just by randomly guessing. However, the probability of it is extremely, extremely, extremely low. Really, 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 really low. All right, so then the probability of success is consistent. Well, yes, because the student's randomly guessing, the probability of success is the same for every trial, which is P, which is the probability of success. And that would be, now here's the part where you got to pay attention. So since there's 5 choices, only one of which is correct. Right here is where you're going to get it from. That's going to mean your probability of success is 1 out of 5 because there's 5 choices, only one of which is right, which is 0.2 if you want to write it as a decimal. Right, that's going to mean that your probability of failure is the complement of that because there's only 2 options, right? Correct and not correct. If your chances of getting correct is 1 out of 5, then your chances of not getting it correct is the complement of that. So Q, which is 1 minus P, is the probability of failure. And that would be 1 minus 1/5, which is 4/5 or 0.8. And there we have that. There. All right, so that one was a binomial experiment. Because we have all of this in here, we can tell that it's binomial. So I should say up here someplace, yes, binomial. There. Yes, it's a binomial experiment, and we've just proven it. All right, now what about letter B? We're going to have a loaded die, and it tosses 5s 80% of the time. Okay, so that's no problem. Probability of success is 80%. 5s is going to be a success, so far we're doing good. We toss the die and record the number of rolls it takes to obtain a 3. Uh-oh, well, we're in trouble here. The problem that we're having is that because it's recording the number of rolls it takes to get a 3, that's not fixed. So you could pick up this die and get a 3 on your second toss, or you could pick up this die and get a first 3 on your 20th toss, right? So you don't have a fixed number of trials. It could be 2, 3, 4, 5, 20, 50. I mean, technically it's possible, right? And since you don't know how many times you're going to be tossing the die, this is not binomial, right? Etc. So you're done. You don't have to write up anything else. Once you know it's not binomial, it's no good. All right, next. The Agency for Healthcare Research and Quality reported that 53% of people who had coronary bypass surgery in 2008 were over the age of 65. 15 random coronary bypass patients are sampled, and the number who are over 65 is recorded. Okay, so let's check it out. Do we have a fixed number of trials? Sure we do. It's right here. It's 15, right? So there's our fixed number of trials. Do we have a probability of success? Yep, right there. Right, I'll yellow it. There we go. And we'll figure out whether we have independence. So I'm betting this one is binomial. So let me type this up. Okay, so our fixed number of trials is definitely on the case. We have the experiment performed 15 times because we're grabbing 15 random patients. And they're independent because their patients are random, right? That's going to mean that the patients have no bearing on each other. As opposed to, let's suppose they were relatives or they're husbands and wives, things like that. The randomness here is what's going to give us our independence, right? Right there. All right, now what is success? Well, they're interested in the number who are over 65. So over 65 is actually going to be our success, right? And this gets to another point, which is failure and success are the terms we use because that's what was thought of when this probability experiment was first thought of. But of course, success might not always be a good thing or a bad thing. I mean, over 65 is kind of neutral, you know, but it doesn't always have to be a good thing for success. So failure is 65 and under, or less than or equal to 65. How about this, 65 or less? All right, now what is X? X is the number of patients over 65 because 65 is over 65 is our success. Now we could have 0 patients over 65, 1 patient over 65, all the way up to all 15 of them over 65. Right? And so realize the potency of what you're doing here. You're changing something from a qualitative variable, over 65, under 65, which is a yes, no, success, fail thing, into a quantitative variable, numbers, right? That's very, very potent. All right, now the probability of that success was the part I highlighted in yellow. That's 53%, and it's consistent because that's what it is for the whole population. So that's what it's going to be for your sample. And that means that this is 0.47 because one take away, here just in case you want to see it, one take away 0.53 is 0.47, right? Because they're complements of each other, the thing we learned about in chapter 5. And that means that this is definitely a binomial experiment, for sure. All right, now what about the last one? A jar contains 5 red marbles, 9 blue marbles, and 6 green marbles. You randomly select 3 marbles from the jar without replacement. The random variables represent the number of marbles chosen. And we're in trouble. And the reason we're in trouble is that phrase right there. That's going to get us into trouble because when you don't replace the marbles in the jar, that means that you're constantly changing the probability as you go because you're losing independence right here. Right? When you lose independence, it actually makes it so you break rule number 2 and number 4 at the same time, right? Because what's going to happen is your trials are not independent, and then your probability of success is going to keep changing because your trials are not independent, because those two things go hand in hand, right? In general, if trials are done without replacement, that's going to mean that you do not have independence, right? Without replacement, that phrase right there gets us into lots of trouble, right? Now, if trials are done without replacement, it's not binomial. But there's a very big but. All right, let me capitalize that. But what if it was 3 marbles out of a factory of 100,000? Like you walked up and there's a vat of marbles, a huge vat of marbles, and you just take 3 out of them, right? Is that a problem? Well, it's a problem if you're stealing them. I mean, this is, you know, bulk bins at Meijer or whatever. People think, oh, if I just take 1 piece of candy, nobody will notice, right? So it is a problem long term. But if you're taking them out to experiment on them and you're not stealing, right? That's not going to be a problem, right? It's not independent, not really, but it's really, 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 really close. And that's because those 3 marbles you take out are so small in comparison to the huge amount that even though it's without replacement, we still kind of can sort of count it as independent because you're not taking enough out to really affect what's left. That idea is going to come back to us in a big way in chapter 9 and 10 and 11. So just keep this in mind. So in general, when you do without replacement, it is not binomial. But if you make it so that the amount you're taking is really, 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 really tiny in comparison to the huge population, then basically we'll fudge it and say, yeah, it's close enough. We'll count it as independent, right? So it's not independent really, but we'll basically say it's independent for our purposes later on. Okay, so that's just a little heads up for what's going to happen later. All right, we'll stop right there. And in the next video, I'm going to show you how to find the probabilities associated with these experiments.